So yeah, today Michel will be giving his third and final lecture of the series. Um, he's a professor of physics and astrophysics at Paul Sabatier Toulouse-3 University. He's a specialist in astrophysical fluid dynamics and has a special interest in rotating fluids. In recent years, he's developed with his team the most advanced two-dimensional models of rotating stars, rapidly rotating stars. And he's also leading the ESTER project that's associated with that work. And yeah, very happy to have you here, Michel.
Thank you, Aaron. So I will start back here. Since last time I was talking about the wave equations of inertial modes, so perturbations which are restored, so or for which the restoring force is the Coriolis force, so perturbations which are associated with rotating fluids. And I showed you that, in fact, if you consider a global perturbation, so a mode, the pressure perturbation verify this the Poincaré equation, which has this special feature of being of hyperbolic nature from for the spatial coordinates, and this makes this problem ill-posed in the sense that since the pressure perturbation must verify boundary conditions, and you know that hyperbolic problems, they are well posed when they meet initial value problem, not boundary value problem. And I showed, so I mentioned this classical wave equation, which is the classical hyperbolic equation, where you specify the initial conditions, and which give the full, the complete solution for these unknowns f and g. And so the point was, yes, I wanted to show you that if you specify, for instance, a perturbation at some time, and you specified again this perturbation at a later time, then your problem is ill-posed in the sense that the initial condition might not be compatible with the final conditions, and especially if there are boundaries. So the one other aspect of this problem is one important lines or one important curves in hyperbolic problems are the characteristic lines. So in the classical Poincaré problem, these are straight lines, and physically they show the path of energy. In fact, they are parallel to the group velocity of the waves. And if you consider that they behave like a dynamical system and they bounce on the boundaries with this constraint that they have to meet in the sense that the angle that they make with the rotation axis is always the same, then you find that the characteristics are converging towards a periodic orbit, which we call an attractor for obvious reasons. And this attractor is actually a singularity for the inviscid case. So when you have, for instance, a wave which propagates, it will follow this attractor, and its amplitude and its scale will, the amplitude will grow to infinity and its scales will decrease to zero. How this is possible, this is what I would like to explain. When we discovered this, we first say, okay, let's have a look to the solution of this eigenvalue problem when we add viscosity, so a process which regularized the solution. And we found that this solution where the amplitude of the mode is focused around an attractor. And to go a bit further on this problem, we analyzed these lines, which are in fact shear layers, oscillating shear layers. And it turns out that in the case of 2D modes, so when, for instance, you can neglect the curvature terms, which means that when you are far enough from the rotation axis, then you can find an analytical solution for these shear layers. And what you find is that the profile of the shear layer is actually described by a Schrödinger equation of a quantum particle which is trapped in a parabolic well. Which means that, in fact, the waves is trapped by the attractor and resist to the attractor thanks to viscosity. So that's an old problem, but what I show here is that this profile of the wave trapped around the attractor, and you see it's just like a mode, and the point is that its width scales with some fractional power of the viscosity, which is here symbolized by the Ekman number. So here, this is the 1/4 power, but in 3D problems, this is the 1/3 power. We have been able to solve this problem in 2D, but in 3D, it's still resisting to us. It's more complicated. There are more scales, and well, so many people have tried, but no success yet. So let me show you why a wave which propagates around an attractor, in fact, becomes singular. So for that, I will consider inertial waves, but what I say about inertial waves would apply quite similarly to gravity waves. I will show you the difference, but well, the difference is minimum. So the point to remember is, so we consider this is the mass conservation, divergence of u equals 0, and this is the momentum equation, where you see here the Coriolis force, and I assume that the wave is a plane wave, so a local analysis. And I derive the dispersion relation, which is here, omega square equal 2 big omega squared times the wave number along z divided by the wave number, the module of the wave number squared. When you take the gradient of this dispersion relation, you have the group velocity, and which is just like for the gravity wave, it's perpendicular to k, so it's perpendicular to the direction of the phase propagation. And you also see that these waves are low frequency waves, since kz is always smaller than k. So omega is always less than 2 capital omega, so which is called the Coriolis frequency. And of course, again, these waves are anisotropic, and so propagate preferentially along the rotation axis. So you see the picture is a bit similar to that of gravity waves. So now what I would like to show you is how such a wave reflects on a plane, on some solid, which bounds the fluid. So on this diagram, you have the phase which go that way and reflect that way. In fact, during the reflection, what is conserved is this angle. In fact, the angle with this horizontal or with the rotation axis, but this axis is perpendicular to the rotation axis, so it's the same. And for the energy, it's the same. The energy propagates along the characteristics, remember that, and keeps this angle constant. So when we try to analyze this reflection, we can derive how the wave number changes upon reflection. And so I briefly show the calculations. Sorry that these slides are in French, but I think it's not very important. So you have an incident wave, which comes like this, and a reflected wave, which is also a plane wave. And what you demand is that the sum of these two waves projected along the normal of the plane is zero. It means just that the velocity of the fluid is tangent to the wall. And then you demand that, well, the time dependence of these two waves should be the same, since they verify this equation, and this implies that the frequencies of the waves are the same. And the other point is that you also demand that the behavior along the plane of reflection is the same for the reflected and the incident wave. And this leads to a condition on the wave number. So this cross product with the normal vector is conserved. And if you project this, then you get this Snell relation between the two the modules of the wave number. So ki sine I equals kr sine r. And of course, you note that if the wave is not dispersive, so if the wave number doesn't change during the reflection, then the two angles of incidence and reflection are the same. This is the very basic law of reflection in optics. But here, you see that these two angles R and I are not the same. If I come back to the drawing, this is the normal, and so the incident angle is this one, and the reflection angle is this one. So you see they are not the same, they differ about 2 times this angle with the rotation axis. And so the consequence is that the wave number after reflection is the wave number before reflection times this ratio, which can be infinite, actually. It can go to infinity, since this angle, because of the way you orient the angles, can be 0. So the thing to remember is that the wavelength changes after reflection on an oblique wall. And the consequence of this is, if I come back to the trajectories of the characteristics, when the wave goes from here to here, in fact, the wave number increases by a factor which is related to the distance, to the ratio of the sine of the angles. And in fact, if you make the loop, you can show that at each loop, the wave number is amplified. So, in fact, in the end, if there is no dissipation, then the wave number goes to infinity, and you have you have a singularity. So you head towards a singularity. Of course, in stars, it's difficult to have pure inertial modes or inertial waves or pure gravity waves, since the stars are stratified, they are rotating, there are a lot of phenomena. And so the thing that we have investigated, well, we have first investigated the influence of the stratification, but I would like to start with another phenomenon, which is just the differential rotation. Star never, I would say, rotate rigidly. There is always differential rotation somewhere. So it was important to know what was the effect of differential rotation on these modes. And the first effect of this differential rotation is to change the nature of the operator. the operator is no longer completely hyperbolic, but it is of mixed type. It means that there are regions here, for instance, in this outer part of the shell, where the operator is elliptic, and so where the waves do not propagate. And as you can see on these two pictures, the wave and here the attractor reflect on the turning surface. So in this case, you see that you don't need the core or the second boundary to make the attractor. In fact, the outer boundary and the turning surface are sufficient to generate an attractor of characteristics and the associated singular mode. Here, that's the same. Here, the turning surface is on the right picture. The turning surface is an ellipsoid. You must think this in 3D. And you see again that it participates to the generation of the attractor. In fact, the first time we saw such mixed type operators, you see also that the characteristics are no longer straight lines, but they are curved. And this is because of the combination of, the effect of the differential rotation, actually. In fact, that the coefficients of the differential operators are not constant. Yes, and associated, yes, with the differential rotation is the appearance of critical layers when you consider non-axisymmetric waves. So in this case, you see that the wave can propagate but cannot cross this layer where the phase velocity of the wave equals the fluid velocity. In fact, at this place, the wave number becomes infinite. That's another way also to generate an infinite wave number and therefore a strong dissipation. I will detail another example with gravity waves in a few moments. So yes, what I was going to say is that the first time we saw these mixed type operators was when we combined the gravity modes and the inertial modes, since both are low frequency modes. And that was the PhD thesis of Boris Dintrans, so now quite some time ago. And what we found is that indeed, in stars, we can have, this is so on the right, you see a 1D model of what could be a gamma Doradus star with a small convective core and a thin convective envelope, and in between, so this rotating, stably stratified radiative zone. And here, what we found to be an attractor and its associated wave function, but well, it's not so clear as in the Boussinesq case on the left. And then, yes, a few years later, we studied the complete picture. In fact, the case when you have a rotating stratified fluid, you can show that there is no hydrostatic solution in the rotating frame. In fact, as Matt has shown, in that case you have baroclinic flow. In fact, what is called the thermal wind in geophysics. So a differential rotation, basically, which appears. And so in the general problem, you have both differential rotation, stratification, and of course, rotation. Well, and as you can expect, the operator in this case is also of mixed type, and you have elliptic region and hyperbolic regions where the mode can propagate. And as you see on this picture, you also have attractors where the waves are focused. In an even more complicated thing, that was a study that Jérôme Ballot did for a rotating polytrope, stably stratified polytrope. So it's a gravito-inertial mode, but in this case, we took into account compressibility, and we find this very strange mode, which we call the rosette mode. 1 year after, two Japanese researchers find very elegantly the way to reproduce these solution, which we found numerically, of course. And it's in fact not so complicated, but they had a very good idea to find these modes, which in fact are superposition of spherical harmonics in some way, which I would not be able to explain actually. But if we have an analytical solution for this mode, you see that then we can this mode sample the star at some very places, and so we can have information of the stellar properties on display. Well, what is shown here is the solution for a polytrope. So, what is what are the solution on real stars and on more realistic problem? They are a little bit more complicated, and as you can expect. So yes, to conclude this chapter on the zoo of waves, I would like to show you two little movies. One which is from a simulation, just to give you a sort of intuition of how these anisotropic waves behave in a realistic context. Okay, so that's what you see here. I've stopped the animation for the moment. So you see a gravito-inertial wave inside a spherical shell. That's one of the solutions that we found with Boris Dintras. And so it's a mode of mixed type. Let's start the animation. And look how the energy and the phase propagate. You see the phase propagate perpendicularly to the rays, and the energy, you can see the amplitude of the wave just whoop, moving like this very rapidly along the rays. You can see it starts here and propagate parallel to the wave. So it's really hard to have an intuitive idea of how such wave behave, but so you see the phase is going one way, and the energy, the amplitudes are propagating the other way perpendicularly. So let me stop this and show you another video, just to show you that in fact such configuration can be observed in reality. And for that I will show you the result of an experiment. So just let me explain what you see on this picture. So in fact this is a container which size is about 30 centimeters in all directions, and which is filled with salty water with some colorant or some color, just to show the motion of each layer, and in fact to show the propagation of gravity waves. The waves are excited by variation of the gravity. In fact, the whole bucket of fluid is on an oscillating table, which oscillates vertically. So the waves are excited by a parametric instability. And this is a configuration where you have a very simple attractor, which I will let you discover. Now I'm running the thing. So you can see the attractor here. This is the place where the motion is maximum. And you see that at some places it finishes by mixing, but you see that mixing with the waves is really hard, even with the attractor. So that was an experiment which was realized in Lyon by Léo Mas and Joël Sommeria, now I would say 20 years ago. So these two experiments, the numerical one and the experimental one, show you that attractors actually exist. And the condition, in fact, is that the container has a shape which is not separable, where the variable cannot be separated. Because you can ask why people have not seen the attractors associated with gravity waves for quite long time. I mean, if you look at the literature in astrophysics, these I would say before 2000, nobody was talking about attractors of gravity waves. And in fact, that the reason was that people used spherical geometry, and in spherical geometry, when the buoyancy is radial, then you can separate the radial variable and the angular variable, and in that case, these singular solutions disappear. But if you mix rotation and gravity, then you break this symmetry, and the separation is no longer possible, and you get attractors. Okay, so now I think I will jump to the last part of my lectures, which is about transport by waves. So that's, as you can imagine, the most difficult thing, because in fact this is a non-linear thing. So I will start first with this picture, which shows you that waves can indeed transport people first. So these are surfers on the tidal bore, which every year or twice a year is going upstream the Dordogne River. And so that's a picture that I made in September 2019. And so if people are skilled enough, they can run on the wave for kilometers. And so these waves are in fact cnoidal waves, and which are solutions of the Korteweg-de Vries equation, just like the soliton waves. And at some places they can break, and some people can fall also. So waves can transport, but of course this is a very artificial problem. If we want to examine the case, a more natural case, the point is that waves are of finite amplitude, and if they propagate on an heterogeneous medium, then the fluctuation of the quantity which is varying in the background can be transported by the wave. And so just to illustrate this idea, I consider a background medium which is heterogeneous in the concentration of some chemical, for instance. And if you neglect the diffusion, then the perturbation of the chemical when the wave passes verify these equations. And if you assume that the wave has a dependence, so a periodic or with some complex eigenvalue, complex frequency, then you can express the perturbation of the concentration with the perturbation of the velocity. And then it's easy to compute the flux, which is generated by the wave. So that's the real part of this product, the complex conjugate of the velocity times the concentration perturbation. And so if you put this, you use the solution, and if you say, for instance, that the gradient of concentration is in the z direction, then you find that the current is proportional to the wave amplitude squared times the damping rate of the wave. So the real part of the wave, which can be damped most of the time, can be amplified also, and divided by the modulus squared of the eigenfrequency. So what is important here is to remember that it's proportional to the amplitude squared and to the damping rate. If the damping rate is zero, if there is no dissipation, then there is no transport in this way. As an example, I would like to discuss the case of a gravity wave which hits, I say a shear layer, but just a moving layer. We just need that actually. And so I start again deriving the dispersion relation, but in that case, I assume that we have a background velocity which is uniformly moving in one direction. And so, in fact, you have new terms. Oh, I forgot something here, AKX times V0. Sorry for that. And what you find is this new dispersion relation. So you see that compared to the original dispersion relation of gravity waves, you just have this new term as a supplement. So what do we do with that? Assume that you have two layers, one where the velocity V0 is zero and one where V0 is non-zero. And you consider a wave which goes from one layer to the other. So that's the point. At the interface, so I assume that the interface is a plane of z equal constant, then the vertical velocity is continuous, the vertical velocity of the wave, because you have to impose mass conservation. In that case, well, it implies that the kx, the wave number, must be the same in both layers. And now if we suppose that the wave is propagating in the same direction as the above layer, I will show you a graph, just the next slide. Then, so it means that omega is positive, V0 is positive, and Kx is negative, so that this plane wave propagates towards the positive x. So at the interface, what you see is that this quantity, in fact, decreases because it was omega square, and then it's omega minus something squared. So this quantity decreases, which means that this quantity has to decrease. So how can it decrease? Since Kx is constant, the only way is that k square increases. And that means that the only way is kz increases. And moreover, if the wave velocity, the phase velocity of the wave is just the velocity of the fluid, then you see that the only way this thing will vanish, the left-hand side will vanish. And so you need to have an infinite z wave number to make the right-hand side vanishing. Now let me illustrate this. So you have these two layers. Where is my pointer? Yes. So 2 layers, I assume that there is a uniform temperature gradient, positive temperature gradient, so that the Brent Weisseler frequency is the same everywhere. So here the velocity is 0, and here it's constant, and there is a shear layer in between, but that's not the point. Assume that there is somebody who is agitating the fluid here, is generating waves at a given frequency. So if the frequency is given, the angle between the vertical or between the horizontal and the group velocity is constant. And so I assume that, okay, the wave is propagating like this, the energy is propagating like this, and the phase is propagating like this. And so when the amplitude reaches this interface, what's going on? We have seen that the Z component of the wave number is increasing very much. And therefore, if we look at the expression of the group velocity, we see that the group velocity reads like kz times n, with kz as the x component and minus kx as the z component. So we see that the z component does not vary very much, so it's positive since kx is negative. But this quantity is increasing. So it means that, in fact, the group velocity is now is closer in direction with the interface. And so is refracted in this direction. It is refracted and it is damped in the sense that the wave number has increased, and maybe it has increased very much. And so, in fact, the wave is dissipating in this layer. And with dissipation, it has some momentum. In fact, since the gravity waves are transverse wave, you see that the velocity of the fluid is perpendicular to the wave number. So it's parallel, actually, to the group velocity. So the wave velocity is like this. So the flux of energy is like this. The flux of momentum is also along the group velocity. And so when the wave is damped, it deposits its momentum in the same direction as the fluid flow. So it pushes the flow, and it tries to increase, in fact, the fluid flow. And this is what we have seen actually in the simulation of Le Cohanet that I showed you in the first lecture. So here we are. You see that waves, they can transport momentum and they can deposit it, but to deposit it, it's important that they have that they are damped. In fact, that the damping rate is non-zero. In the adiabatic situation, you cannot transport momentum actually, because it continues with the wave. So another way to transport chemicals and momentum is the so-called Stokes drift. The Stokes drift is a purely nonlinear phenomenon, and in fact, it's the displacement of a Lagrangian particle when a wave passes at the place of the particle. Maybe this is something that you have experienced when swimming in the sea. You have seen that the waves which are moving to the shoreline are moving you a little bit towards the shore. And in fact, the closer the shore you are, the stronger your motion is. And if you go to the far from the shoreline, then your motion, the impact of the wave is very small. So let's try to understand what's going on. In fact, the motion of a particle is just the integration of the velocity field times dt. But the velocity field depends on the position of the particle, And this position depends also on the velocity. So you see, this is a strongly nonlinear problem, which you can not fully solve, but you can get a very good idea of this effect if you consider that the motion of the particle is small compared to its position. So you can develop this, and what you find is that well, the motion of the particle is, of course, this displacement plus the integration of psi times the gradient of the velocity. So to illustrate this, I will consider surface gravity waves. So just like a swimmer on the shoreline, how does these waves transport a Lagrangian particle? So we have to remember that for surface gravity wave, the flow is irrotational, so you can write V equal grad of some potential phi, and this potential phi, in fact, reads like some function of phi, which is an exponential, times the exponential of I k x minus I omega t. So I assume here that it's just a 2D problem, just to make it simple. Then you assume that the water is incompressible, and so phi is a solution of Laplace equation, which means that the z dependence is just an exponential. And since I'm considering that the water lies in the negative part of the zx plane, so I just consider the exponential kz component or solution. Okay, and then once you have the potential, then you can derive the velocity component. So Vx, which equals Ik times this, and Vz, which is the d phi over dz, and which is k times this. The important point here is that the two components, the x component of the velocity and the z component of the velocity, are in quadrature, so are phase shifted by pi over 2. This is important because the motion depends on this phase shift. In fact, this phase shift is the same for the displacement, for psi x and psi z. And here I took the real part, and so that this is why you have a sine and here a cosine. And then I have to compute this quantity, which is in the integral. So it reads like this. In the x component and in the z component, this is 0. So then if we report this in the integral, we can derive the drift velocity of the flow by just deriving with respect to time the displacement. And we find that the drift, oh sorry, I forgot that there is Ex here, the unit vector, it's along x. So it's omega times the wave number times the squared amplitude times this exponential, which shows that the drift is at constant speed and decreases exponentially below the surface. So in fact, the particles which are floating at the surface of the water are moving most rapidly and more rapidly than the one which are in between two waters at some depth. To illustrate this, I found that video on the web, which I thought it's quite clear to illustrate. Okay, so on this video, This is a wave packet which is moving from left to right. And you see these red objects, which are Lagrangian particles, one on the surface. And so their trajectory is registered on the right one. And since the wave packet is passing, the amplitude of the waves is growing and then diminishing. You see that the amplitude is very large. In fact, it's 5 meters between the minimum and the maximum. And so you see that the particles are just oscillating, but slightly moving from the left to the right, just as predicted by what I have shown you. So now let's do some numerical application. As you know, I live in Toulouse. This is not so far from the Atlantic coast, and where we can experience some strong gravity waves. And so I used the realistic numbers to compute what was the drift velocity of a particle which was quite far from the coast, and so where the depth of the ocean is much larger than the wavelength of the waves. And what you find is that this drift velocity is quite small, actually. So it's a 1 meter amplitude, so it's not that much, but this is a reasonable amplitude. A period of 10 seconds, this is also quite typical. And you see that a Lagrangian particle would move to the shore with 6 millimeters per second, which is half a kilometer per day. So in the end, it's not negligible if you consider a long time span. Now, of course, if you are on the beach or near the beach, the things are a bit different. The dispersion relation is different. And if you put the numbers, then you see that you have much higher velocities for waves which have the same amplitude, but on a depth which is about the same. So that's for the Stokes drift. So in fact, I would like here to give some conclusions about wave transport. In fact, what we have seen is that what are the quantities which matter for wave transport? Of course, the amplitude of the wave is important. It's the transport varies with the square of the amplitude. But another point is that the damping of the waves is important. In fact, more generally, the dissipative processes are important. The background anisotropy or inhomogeneity is also important. If you have an homogeneous background, you don't transport anything. And the last but not the least is time. Obviously, the transport by wave is a slow process. This is a slow process, except for shock waves, of course. Shock waves are quite violent. But otherwise, if you go inside stars, amplitudes are small, even very small. The damping is weak. And then, well, the waves carry both heat and momentum. Just remember that. So what they can do is to change the temperature distribution and the momentum distribution, or the angular momentum distribution, for instance. So the conclusion is that waves need time to be important vectors of momentum, heat, and chemicals. So they transport everything, but at a slow rate. And in fact, this slow rate is making the major difficulty with to evaluate what's the impact of the waves. In fact, yes, so that was my point, is that the waves can be important on long time scale, and that makes the problem complicated. Why? Because on long time scale, you have many slow phenomena which come into play. And for instance, like atomic diffusion, this is a slow phenomenon. You have tiny flows like meridional circulations, which are generated by baroclinicity, or angular momentum losses, which, by viscosity generate Ekman circulation. So all these are flows which are of small amplitude, and if you add waves, well, they will compete with these tiny flows, and it's hard to know who will be the winner, and there may be no winner actually. In fact, they will all mix, and so in fact, if you don't take everybody into all these phenomena into account, you might not go very far. This is why I said hand-waving arguments usually do not go very far on this problem. And more dramatically, if you are using a simplified model, then it will be likely oversimplified in the sense that, okay, you can understand what is the action of waves, but if you consider a more realistic model, then you will have phenomena which are as important as the one you are considering. So, in fact, the result that you have found with this simplified model might just be inoperative if you consider a more realistic model. Okay, so that's a challenge. And to give a final conclusion to these lectures, I would say that there are exciting problems with waves in stars. And first, I list a few of them. For instance, we would like to know how shockwave can expel matter out of stars. And for instance, at the end of the giant phase, when the degenerate core remains naked. How is that possible? Waves, one thing is to try to represent the mean effect of waves. So how to design mean field models where you can represent the stresses, the momentum, so the momentum transport, the chemical, and the heat transport by waves. We know, for instance, that from numerical simulations that the transport of chemicals is, in the first approximation, can be seen as diffusive, but the momentum transport is never diffusive. So, so if you don't want to take into account the whole details of the wave, if you don't have the time to make a DNS, the question is how to represent the action of the waves in a mean field model, just like for turbulence, actually. One thing which is still not clear is how this frozen-in convection works, and what would a direct numerical simulation say about this excitation of gravity waves in gamma Doradus stars? We can think about surface gravity wave which break at the surface of stars and launch matter in space, and this is a scenario which is supposed to explain the BE phenomenon, where we have stars which are rotating close to the breakup limit, but at the moment, I don't know anybody who has shown how the matter could be launched in space by waves. But this is something to investigate, and there are many problems. So the final conclusion is that waves indeed matter in stars, And first of all, because they are probing stellar interiors, and thanks to them, we can have precise ideas of the physics of the interior and the temperature field, density field, and etc. All the physical parameters which are probed by waves. And finally, we suspect that they have a true impact on the internal dynamics of stars. This is still an open subject, and because this is a difficult subject, because of what I've said, this is the impact is slow, needs a lot of time, and therefore you have to take into account all the slow phenomenon, the weak phenomenon, which combine and which also impact the evolution and the chemical evolution and the dynamical evolution of stars.